rough timeline so that I can work with our internal team. So
okay,
just,
that'd be great.
yeah, just
All right.
preparation. Yeah.
So there's two efforts going on now. We've got to a model where I think I've got the thermal design, at least the prototype, covered for the University of Illinois Champaign-Urbana. The conformally coated copper guy, researcher. So he said he had some budget there, research budget, where he could do some testing. So so hopefully we'll build a module with that based on that.
Stay on Lawrence Expressway.
Oh, good morning. Good morning, John. Good morning, Jingfu. Let me just capture these people.
No,
Jingfu, is this your first time here, Jingfu?
Yeah, this is my first time.
It is your first time. Could you add your last name by chance so I can just record you to your Zoom?
Sure.
Okay. Yeah, so also Load Slammer, Roger Beeston from Load Slammer is doing a Load Slammer package based on the VP 1902 from AMD, which so we're gonna design a module with that one. So that will be, so he'll have a Load Slammer, so we don't have to buy the full FPGA at many thousands of dollars. And that will be what we will use to load give the thermal load for the cooling tests with the University of Illinois Urbana-Champaign. And the other project is with IABRA, where my God, I'm useless for names this morning. Greg Compton. Greg is as he announced on one of these calls. He's in partnership with a large European defense company where they're setting up an AI skunk works for the defense area, and he's gonna start building some modules around this as well. So they were still just finalizing the joint venture or whatever it's called. But that's imminently closed, I believe. So hopefully we'll get started on that. But in all honesty, Michael, I suspect real modules will be sometime next year. Hopefully we'll get going at a fast clip when these guys bring some funds into this.
Okay, that's good information. Okay, thank you.
All right. Okay, hi Mitch, how you doing? Right, let me just capture these people. So we're
morning, Alan. Doing well, thanks.
Good. Once I've called these people, then we can get going. It's 8:06. Thank you, Jingfu, for adding your last name. Let's just put you in the records. Okay. All right, let me share my screen. Just find my way around here a minute. Share screen, there it is. My main desktop. Okay, so let me just update this. I'll sort out later. Okay. All right. Well, welcome everybody. So today, we've been making some more steady progress. I've got a lot of discussions going on with a lot of people. So there is a lot of interest in this module now from many angles. So I'm more and more hopeful that we're plugging in the right direction. Today I've got a couple of burning things. I'm going to be on a lot of travel, and I'm going to be talking about the OCP HPC module with these various people in different guises, I guess, in terms of what this can do, or what we can potentially do with our efforts. So I'm going to focus today's meeting really on bringing you up to date with that, and specifically the OCP HPC Summit. I wanted to just go through the philosophy there, and maybe review the slides as they stand right now, and just get some feedback from you guys if there's anything I'm missing or the tenet I'm taking. I'd appreciate feedback on that. Also, I'm hoping that we're going to be in the experience center, either the composable memory systems experience area, or the ODSA area. I think we might be in the composable memory systems area. So I'm just nailing that down, but we might have a small desk there where I'll be able to show off 3D models and actually just talk to people about what we're up to. So I'm hopeful that will come off, and we are currently printing some 3D models as well. But before we get going, usual introduction to new attendees. So actually, if would you like to give a brief introduction, Jingfu? Of
Yeah,
yourself?
sure. My name is Jinfu Huang. I work for Inventec. Inventec is a server ODM company in Taiwan. We manufacture server for a lot of big companies like HP, Dell. So I'm interested in the hardware of this HP. That's why I joined this.
Sorry, you broke up just at the end there. Why are you joining us? Sorry.
So I'm a hardware engineer in my company, and we recently want to participate in the OCP to know what's the trend and the latest technology. That's why I'm hoping to attend this meeting.
Excellent.
Thank you.
Okay, welcome aboard. Thank you. Okay, so starting with the presentation, let me see if I can bring this up. So I've got these slides that I submitted. I'm not fully polished yet, but I've got the tenet of everything, and so the animations might not work because I do rely on them. But let me just walk through. So can everybody see the first slide? Can you see this okay?
Yep.
So the title of the presentation is HPC, the Next Generation, a Sustainable Energy-Centric Architecture First Innovation is what I've titled the presentation. So just as a backdrop, the presentation I gave, would you believe, 2 years ago now, was a detailed technical dive into the various aspects of the module and why it brought power delivery efficiency, signal integrity improvements, etc., etc. All of the modularity, the composability, all of the features that would allow somebody to build a very efficient machine. And if you remember way back then, we were trying to be driven by specific metrics, but in the end, it's we've just there's so many aspects of this. It's difficult to measure any individual one. So because it's a system effort across all the pieces. So that was a very technical dive. But in speaking to people over these last 2 years, it's obviously very difficult to get, especially I've only got 15 minutes, by the way. So it's very difficult to get into the weeds, and you're going to lose people at such a fast pace. So I wanted to really focus this presentation on the why, and what's driving it. And obviously, the focus is sustainable energy-centric computing is what drives all of our decisions in this architecture. And so that's really what I'm going to drive. But I'm going to also talk about the trends of the industry, what we're seeing, and how we need to do more of this in the open. So here it goes on the slides. This is a second introductory slide. I'm not sure why they do this, but okay. So my first kickoff slide is proprietary computer architectures are prolific, and so I've just taken a couple of snapshots of these. We can see that these are beginning to diverge significantly from the standard server architecture we're all familiar with. And the question is why? It's all about, it's always about performance, but it's also about energy as well. And because energy has always been a focus of anybody designing a piece of silicon, but it's usually hidden in the background. It's not in the foreground. And so if you look behind the hood of all of these architectures, energy is a key driver to these bizarre architectures. And at the end of the day, the problem is they're proprietary and they're locked and loaded in these huge companies, and you can only use their silicon in their architectures. So it's locked out to the rest of us. And any new startups with new silicon just can't play in this field. And that's a big issue. And this is where OCP comes in. So, but what is driving computing architecture? Obviously, we always want performance, but really what's driving our industry today is sustainable, power and cost efficient, and specifically domain specific architectures. So just looking at those one at a time, from sustainability, we're always demanding more performance increase. And thereby, by default, we're improving energy efficiency. We have to, because the power density is so great. And we're now looking at energy recovery. That's becoming a big topic of, can we reuse the heat from these machines? In terms of sustainability, just looking at that side of things, it's under 3 scopes. Most of us are very familiar with scope 2, the power consumed by the machine itself. But there's scope 1, which is the facilities, the power needed for the facilities, etc. And a biggie that people are focusing on these days is the scope 3, which are the embodied carbon in the machines themselves. And so we need to look at all of those. That's sustainability. Domain-specific architecture composability is where you can compose your different architecture to suit a particular application and run most efficiently for a particular application. I've shown these 4 categories to show how that exists today and where it's going. The mobile phone is the epitome of a real fixed architecture where everything's been compressed into one piece of silicon with a huge market for it, and it justifies that investment, but it's definitely fixed. You're not going to compose this, or it's going to take you years to recompose it for different applications. But that's fine for mobile phones. In the other extent, we've had decades of the server, which is about as pluggable as you can get. Everything from the memory to the processor, to the storage, the accelerators is pluggable. But sometimes these resources can get stranded. Then we've got this hard physical composability that's emerging, where we're literally sucking that server into a package, where all the memory, the processors, the accelerators, the IOs, all embodied in one package. But the problem is, it's a pretty hard physical composability. You're not going to plug these. It takes millions of dollars to put these different die together. So I've called that hard physical composability. And then we've got at the other extreme, the dynamic software composability, where we put all the resources in different drawers and the software guys reattach everything together and use the resources exactly as needed for each application. When we look at this from an energy perspective, the chiplet approach is all about energy efficient hyperconverged chiplets. We've got a hyperconverged architecture here, 0.5 picojoule per bit. When we look at the software world, it's extremely energy inefficient as it stands today. In these disaggregated racks, we're in the region of 20 picojoules per bit to move stuff around right now. But standardization is driven by CXL and Ultra Ethernet consortia, These are the two big standardization efforts that are going on to hopefully, well, they are making this possible. And the standardization driven in the chiplet world is our own OCP ODSA subproject and the UCIe consortium. And there are a couple of others in the background there for the IoT space, etc. So there's efforts going on. So that's the world of composability. But we could really do with the hardware guys at the chiplet world talking to the software guys in the dynamic software composable world and bringing these two worlds a little bit closer together. And that's what OCP HPC is all about. And to hammer that point home, Google said when their TPU v4 system architecture matters more than microarchitecture. And they gave a few presentations at Hot Chips just a few weeks ago. It's fantastic what Google have done there. And this is a mantra a drum I've been beating for many years. And it's nice to see the big boys start to publicly talk about it. So we've got those two. And finally, it's all about cost. And if we've got an open architecture, we can really drive down the cost. And that's what OCP is all about and why we're here in the OCP High Performance Compute Subproject. So this is what's driving, this slide shows what's driving computing architecture and what we're all about in the OCP HPC subproject. So let's take a little bit of a deeper dive on the technical side. So domain-specific architecture, I created this template a number of years ago, and there is a presentation where how I came up and concluded with this slide. But I believe this represents a nice abstract view of the future of computing architecture. It's all about tiered memory. We have what I call a data plane continuum, and a machine running an application will be constructed. The application will be distributed across the cloud, the edge, and the IIoT, depending on the application's needs. And so this is a great template to start with when you're constructing a domain-specific machine for a particular application. If we dive down into the individual building blocks, domain-specific architecture building block, and again, this is an abstract view, we have our high-performance processors and accelerators, and we really want to attach more and more memory to these things, volatile, persistent, file system storage memory, all of them. But one of the key things is we want ever-increasing bandwidths at low latency and ideally at really low energy. So I call that, sum that as a local memory interface. And but if the main processor doesn't need those resources, we really want to be able to share those resources over a high bandwidth memory pooling data plane. So this is a simplicity of what I believe the direction that we're going in. There's obviously a lot more detail behind this. But if we map that single block onto our big architecture diagram, we can see that we've got our processor, its own local memory, and the sharing bus for sharing it with everybody else. And it doesn't take a genius to realize that you can step and repeat this module many times to start to build this architecture as a whole. And essentially that's what we're trying to do. So in a physical world, we're creating a module like the abstract module, and we're creating many of them in what we call a wall of compute. So this, and then this wall of compute, so the order of these slides, guys, is maybe a little bit, I need to change the flow of this, but these compute modules can be configured for different nodes that we're already aware of today, like a dual frontier supercomputer node, 4 GPUs per CPU, and we wire these exactly as the frontier node is wired. We could have a tightly coupled CPU and GPU. We can make a Grace Hopper configuration by putting two modules together and having a lot of bandwidth between them. We could make a Summit node, the Summit supercomputer from 2018, IBM and NVIDIA, with 3 GPU nodes per CPU and specific wiring. We could do a GPT-3 optimized one with all AI. We could do a pool if you really wanted to stick to the dynamic pool, the pooling disaggregated pools. We could make an FPGA pool, or we can have a Burger King, compose it your way. So here is a module just exploded. I'm not going to go into details, but you can see that we've got some cooling infrastructure around it. The PCB has many IOs. It's more of a backplane than a mezzanine, and you have your big processor mounted on the module. This is inspired by the OAM format, slightly larger width-wise. And then we have up to 16 E3.S modules being able to be plugged in, and they are conductively cooled into the water flowing through the module. So that's how that module is made up. And then you can see that the modules on the wall are all step and repeated in what we call a wall of compute, replacing the 19-inch racks in the data center. So why is a wall of compute energy-centric computing? Well, it does, from a sustainability, it does address all of the scopes, reduces operational emissions. We have direct hot water energy reuse. The whole design of this is direct hot water, where we have a consistent temperature out. So it can be used for energy reuse of 65 degrees C or higher. We have a lower power consumption because you can construct any domain-specific architecture. You can wire heterogeneous modules exactly as your application needs, with as fatter pipe or thinner pipe as you need, and not have to go unnecessarily through switches. You've got less data movement as a result, and you can save a bunch of power there, but both the less data movement because of the domain-specific architecture, but less data movement because these things are very tightly coupled together, so we could lower 10 picojoule per bit channels down to around 1 or 2 picojoules per bit. And we have a much more efficient power delivery process from the AC 270 volts or whatever is AC down to 48 volts into the modules. And from indirect emissions, these modules are constructed exactly the same, no matter what processor they are, and so they are repeatable. All the resources are used, and they can be stepped and repeated. So if you needed to upgrade a piece of silicon, you can unplug the one module, just change the silicon in the PCB, and just reuse all the mechanical infrastructure again and put it back together. So hopefully this will have an upgradability. You can upgrade certain components rather than the latest machines. You just replace them holistically, and you can actually reuse, rather than scrapping modules, you can reuse many of the components with new silicon. Here's a little bit now in terms of, so that's the sort of vision of where this could go for supercomputing. But we also think this will be a great prototyping and enablement platform, and probably more in its early years. And so CXL enablement prototyping platform, I've shown 4 modules here that we would have in a sort of a benchtop, a researcher's benchtop configuration. And then I've got a top-down view, just showing the wiring that you could potentially have, and a side view as well. So we could create 4 modules. These are just 4 example modules: an AMD MI300, an AMD AI FPGA cap device, an Infabrica CXL Ethernet switch, and an Intel Agilex CXL FPGA. And they could be interconnected either with copper cables or with near-packaged optic active cables, or co-packaged optics, silicon photonics I/O as well. And on that note, I was talking to Intel in Air Labs on some of their new products that they've been showcasing over the last few weeks. And they're interested in investigating what we're doing here. And then we can plug in the various different types of media. And as Michael's just said earlier, we've got them either Micron CXL.mem devices, Samsung ones, or their smart SSDs, which have CXL protocol, or just a regular NVMe SSD, etc. Also, we have the ability to, we have an opportunity for chiplet enablement prototyping platform. And we've been talking to, I've been working with the ODSA, and we've been talking to the DOE, etc., about possibilities of how we get chiplet enablement beyond the big guys just doing it all themselves vertically. And one thing to observe is that when you look at a traditional package, these chiplet packages are getting huge now, and the actual HPCM module isn't that much bigger. And we're also seeing power get sucked onto the package as well. So why not cut out the middleman and get rid of the package and actually make the module itself? You get rid of those horrible solder balls with their poor signal integrity, and you've got high-speed connectors with good signal integrity. So this is an idea here, and we could even place chiplets close to connectors, I/O chiplets, for example, and actually get down to maybe half a picojoule per bit on going to pluggable active cables. So we could reimagine redrivers, etc., in terms of the energy needed in the distance that you need to move. So this is where I'm going a little bit. This is a summary slide, I think. So we've got an opportunity to redefine open computing architecture delivers on sustainability, the easy construction of domain-specific architectures, and democratization by lowering barriers to entry and reducing costs. What I mean by that is companies like GraphCore and Samba Nova don't need to build a complete data center. They can just bring their silicon to the market in an HPCM module, and they can plug into all this open infrastructure we've just created. And so it will be a fantastic way for startups to be able to have a chance of competing with the big incumbents. We've also got an opportunity to create a CXL chiplet enablement platform. And really, HPCM brings multiple sustainability benefits: reduced embodied carbon and less raw materials, and improved reusability, improved power and signal integrity and efficiency, seamless silicon photonic enablement, path from copper to MPO and CPO, and simple and effective heat energy recovery and reuse. But we've only just started. We need an awful lot of help. We need broad industry across discipline collaboration, from thermal to power to electrical, mechanical, software, system management, and test. And we're targeting top CXL and chiplet enablement platforms within a year. Benchtop within the year. And please come and join our sub-project. We meet every other Tuesday at 8 a.m. Pacific. Thank you very much. So there you go, guys. That's what I was going to present. How does that seem? Is that good, or missing technical detail, or too flowery, or?
Very good, Alan.
Looks
Particularly
great.
particularly the intro. I mean, the whole thing. How many slides total?
It is a total. I need to probably be a bit more succinct and less waffly to get it in 15 minutes.
Yeah, how many have you got?
I got 19 slides. So
oh man, yeah, no way. So let's say you got 2 minutes, which is
yeah,
pretty
2 minutes
low.
a slide. I know. I mean,
2 minutes is slow. And we usually used to go 3, but for this thing, it's a rapid fire, and they want to see details. So 2 minutes a slide.
I can be more succinct on some of these points. I that's where I need to rehearse.
The nice thing is that all the decks will be posted, so you can put some technical detail in, you gloss over in the talk, but people can go back later and pull out of it.
Yeah.
Oh, you mean in the sort of side notes, you mean, John?
Well, just details in the slide that you don't have to actually talk to.
Oh, right. Yeah, good point.
Everyone that won't be able to attend the presentation, everyone, I'm always looking for, I agree with you, John, that always looking for those details.
Yeah, and leave some of the details on the slide, but when you rehearse, just make sure that you kind of, don't go over, don't dive into the details, but anybody who gets the deck after the fact can.
Right. Okay.
Like I wanted to know, actually, while you're giving the pitch, was do you have a swag at the layer count on the backplane?
On the module? Yeah.
The backplane.
To be honest,
the backplane.
I've done so
on
many
the backplane.
On the backplane, you mean on the module, you mean? This
well,
module.
You had the back. Yes.
This
yes.
thing.
Right.
Yeah. So I've done this. I've been involved in these boards for a living, and also worked with with a company, as you know, Mitch, which has very extensive interposer capabilities. There are a number of issues, like the connectors can't have mechanical holes on them, so therefore there's mechanical issues of tearing them off the boards. But the infrastructure, so there's lots. This is the thing about it being a system design. It's it's knowing the problems with everything and the problems it causes with the neighboring silo, and then well, okay, what can you do to ease the pain on both sides? And so we're not going to have any holes, mechanical holes through the boards, and actually, it's all transceiver based. We are not. If you look at the history of this, one thing that we don't do is support parallel memory. We assume if you want parallel memory, you've got on package memory. or you're using CXL memory. Or I was trying to push OMI, a low latency serial memory, but nobody is picking up on that yet. We'll get there. Give people another 5 years, we'll be there. With CXL, there'll be a low latency version. But yeah, so I'm assuming that there's no parallel buses. This is all serial, which does help in the routability, Mitch. And this is all going to be HDI, and which we've done, you know. So it's the substrate is a big question for sure. But I talked to IBM substrate experts. I've talked to Fraunhofer, and I talked to a few others, and also Bill Chen, who's the IEEE guy on heterogeneous integration roadmap about substrates. It doesn't look like this is insurmountable. The problem is the US only has 5% of substrate capability. The rest is in Japan and Taiwan, right? And so we need to deal with that, but hopefully the CHIPS Act will help us sort that one out. So I'm fairly, if there's an area I'm relaxed on, Mitch, is that one. The co-packaged optics, I threw some crazy ideas out there, and I'm beginning, I can see the photonics people from the Electronics Resurgence Initiative. They're desperate for a system platform that they can start to bring their experiments to and run real system applications. And
Yes.
current server architecture doesn't work, and they're looking at OEM.
I get it. Some of them don't know it. They don't actually know that they need a new platform. Others kind of know it, and there's not a platform. So it's known. Sorry, I think I have some network issues. I missed part of your reply, but I might know something about some of the details on the first slide about how some of that's done. And yeah, there's some pretty substantial PCBs stack ups, not the multi-chip module piece that you're talking about, but the backplane piece. But at any rate, those are, as you know, like you said, those are the devils in the details. One affects the other, sort of thing.
Right.
But
okay. Let me stop sharing a minute. I'm losing. Okay, so we still the same people. We didn't get it. Oh, Victor. Hi, Victor.
Hi. Yeah, I'm here just to watch on her.
Yeah, no worries. I just want to make sure I capture everybody. You've been on before, haven't you, Victor?
I've been here before.
Okay, I seem to have. Let me just make a note. I can't find you at the minute. Okay, all right. So, any other comments before? Well, thank you, guys. So it sounds like it carries the message. I guess is the feedback I've got, but I've got to be careful on the time.
Yep.
Unless I can persuade John sorry.
Very good, Alan.
Thank you.
Like I said, very far down the road from 2 years ago.
Thanks.
Lots of progress.
Maybe I can persuade John to get me a little bit of a bigger slot.
Yeah, don't think that's going to happen. Everybody's pretty much getting 15 minutes. And
yeah, I know. No, that's all right. That's fine. I'll
actually no. So actually, wasn't it? Is it 15 or 20?
It's 15, I believe. And there's 2 or 3 minutes handover in that 15 in the last message I got. So it's going to be tight.
I know our, at least especially CMAC, he wants to accept everybody and then shave the time down. Luckily, OCP didn't let us do that this year, so I thought that there were.
Good. Yeah. I mean, I think the OCP server one that has probably the shortest time of everybody. Everyone else has got about 50 slots. 15 minutes, but anyway, that's all right. No, I'll make it work. All right, so let me just go back to sharing the desktop, and let me switch back to that. Okay, so Yeah, I guess I touched on the 3D model in the Experience Center. So hopefully the composable memory system guys, I got feedback there. Hopefully I'll be able to get a corner of a table somewhere there. And I just need a little space to show the 3D model. I thought when you have it in your hand, and it's we'll have it in pieces that you can sort of put together. Then people can get an appreciation for actually how big it is. And I'll have some. We're doing more simulations. So the little animation you saw, we're going to hopefully have one of the entire wall being populated. Was what we're working on, and I've got a few other ones as well.
Yeah. So Alan, back on the timing.
Yeah.
That didn't sound right. So yeah. So this is you're on the schedule from 12:50 to 1:10. So there are no 15-minute.
Oh, right.
Slots this year. They're all 20. Now there is the couple of handover minutes there.
Okay, all right.
Slots are 20 minutes, and that's what last year we did a lot of 15-minute, and it just too much with the handover, so they didn't let us do that this year. So they're all 20-minute slots.
All right, perfect. Okay, well, thanks for that heads up, John. That helps me considerably. Okay.
Yeah. So who was saying it was 15 minutes?
I don't know. I think it was maybe I got it stuck in my head where maybe one of the meetings we were talking about it, like you were saying, they were doing, maybe Simac was pushing for the 15, and I just got it wedged in my head that was what it was.
Yeah.
So,
you can see it all in the online schedule. If you've been up in the online schedule to look at that.
I have been on in the past, but yeah, I didn't. All right, perfect. Maybe I assumed there was a 5-minute. Yeah. Anyway, whatever. Okay. That's great. All right. I heard the messages separate. All right. That's good. That's good. Okay, a couple of other topics. So I'm actually I'm going back to the UK for a couple of weeks, specifically my hometown of Bristol. Those of you that don't know, it's been fairly heavily involved in high performance computing for many decades. It's got a fairly significant defense in sort of homeland security, national security effort centralized around the west of England. And in fact, there was just an announcement from the University of Bristol, their new high performance compute machine that they're installing shortly. Anyway, they have a technology festival every year. And I've managed to, in fact, I do need to let, I'll be sending a message to the management of OCP that I'm doing this, but I've managed to allocate some time for an energy-centric computing panel, and it's titled, a little bit colloquial, but it's titled "Making the West of England the center of it," or what the title is now. Let me see if I can see it. Get you the exact title. Making the West of England the capital. So it's basically, there's a few things going on in Bristol. In UK and Europe are obviously a little bit further ahead politically wise in sustainability and the energy recovery. You can't build a supercomputer, an HPC machine above a megawatt without having to have at least 10% of the energy being reused. So you won't be allowed to build the machine unless you have that. So there's a lot more drive there to force companies into the energy reuse. And in Bristol, there is a city heat network. So you have hot water going underground, and they've got various mechanisms of getting that hot water in. And so I was proposing that potentially these HPC data centers or even edge networks could contribute to the Bristol heat network. And there's other things in building infrastructure, edge compute, and all of that. So basically, we have a panel debate. I will be going over a subtly different version of this presentation, thinking about the infrastructure in the city planning side of things. And we've got panelists from the city. Greg from IABRA will be joining me on the panel as well, giving his perspective from the defense and AI perspective. So that should be a good event and should give us a nice profile over there. And you never know, that might kick off some efforts in helping us get the ball rolling here. Additionally, at Syracuse Research Corporation, SRC as they're called, I've known about them for many years, decades probably, but they're almost part of the government the way I see it. They provide a lot of contractors to DARPA and the DoD for various things. And when I met the CEO at the ERI summit, and I was mentioning that, you know, because I applied to be a DARPA program manager to try and run this, but based on Paul Hartke from Xilinx's recommendation, he was nagging me for a couple of years. But I got turned down because, you know, they don't see it as hard, and it's not DARPA hard. You know, DARPA is material science hard, but it is hard because it's across all the system silos. It's really hard. So I had a bit of a moan to this SRC CEO, and he said, "Well, we specialize in systems." So he invited me out to speak to them, and I'm speaking to them on Thursday this week out in North Carolina. So I'm making my way out there. And well, we'll see where that goes in terms of potential to get government assistance to get the ball rolling a bit faster here as well. So that's everything for an update. For the first time in a long time, we've actually got 15 minutes spare for any other business. So is there anything anybody would like to pull the thread on a bit more? I just seen in the chat. Mitch is asking, do I have a swag at the backplane layer count? I'm thinking, in all honesty, Mitch, I'm thinking that we would want to be in the region of 16 layers. But we at the board is currently specified as 2 millimeters thick. So we could get up in the 24 layer count if we needed to, but I'm hoping to avoid that. Maybe the power planes might cause us to go in that direction.
No, that would be, yeah, that'd be fantastic. That'd be great. That wouldn't be a, you know, plus 40 plus type thing.
Right. And good to see you're an OCP member now, Mitch. That's great. With Liquid.
Yeah, yep, Liquid. I got them signed up.
Okay, great. All right. So yeah. So in terms of, is there anything else people would like to cover?
What are we doing about optical connect here? Anything?
So the only optical connect we've discussed is when I think I gave one of these meetings, I represented or I played the video of the ODSA when I talked about chiplet enablement, and I showed some cartoon concepts of what I felt what we could potentially do with a migration from copper to co-packaged optics and near packaged optics. I think you probably remember that one. It was obviously uninformed. I spoke to the CTO of Ayer, Mark, can't remember his last name.
Yeah.
And he said, yes, I am maybe a little bit misinformed on some of that.
Yeah, there was a whole presentation like a couple of days ago from OCP on optical interconnect for sort of AI stuff.
Oh, could you send me a link to that, or could you put it in the chat?
I think I'll just be the OCP. Yeah, I'll go look for it.
Okay, thanks.
I'm thinking the future is more optical.
well, yeah. So, so in that sense, we're by us having this, we've got rid of the motherboard and we're cabled everywhere. You know, we can go to this. Is the beauty of this, and this is what's interesting. The likes of all the optical people that I've been speaking to, and so, well, the nice thing is I've got Intel in Ayer's ear, and now they've got this module that they've put in a PCI card, and they want something more deployable, usable, and scalable, so to speak. So I'm hoping to make some progress there. But yeah, you're right. We need to dig in a bit deeper on that.
So please send along the OCP presentation. I thought I saw something, but I missed it. But very interested in that if there's a good presentation somewhere. But however, you know, Alan, every of the systems that you have on that slide, which is the first slide,
yeah,
there, if it goes optics, it completely refactors the cooling system. That's the learning from Terry Morris and 15 plus years
Right.
productizing
and
photonics.
right.
Right. So you just look at this. If you use a Cebra system up to the 17,000 watts, if you go, the first thing it radically changes is the power density and the cooling solution.
Right.
So then it's a whole new form factor, a whole new system.
Well, and that's the thing, isn't it? So the idea here is we are thinking of a future world of optics. I mean, obviously we can go to, maybe the world will go to an optical motherboard PCB, but I'm thinking cables is where it's all at right now. Where we're at the moment is QSFP modules or QDD or OSFP modules, which are huge, but silicon photonics will be much lower power. So can we get those down into these small electrical connectors with these tiny fibers coming off of it? So, we can imagine a rat's nest of one of our walls of compute here, of copper cables. But things could be a lot more manageable with optical ones. So I'm the nice thing about me is I don't know what I don't or what I don't know about optics, so I can ask the dumb questions. Why can you do it like this? And often you'll get an answer of, well, we've never done it, we've never had to do it like that. That doesn't make sense. But could you? Well, maybe we could, but we'd have to re-architect it or whatever. And I am beginning to get that feedback of so what people say are crazy ideas are just they've never thought about it that way, rather than it's not possible.
Yeah.
And it's so I'm beginning to I certainly lit up the Electronics Resurgence Initiative. There was a workshop on silicon photonics from all the experts in this country, and you could see they were desperate. When I mentioned the fact of what we're doing here, and it could be an enablement platform, I mean, they all got excited. They're desperate for how to plug their experiments into a real system, fairly low cost and easily without having to change everything. So, and they did mention that they did try the OAI chassis. They spoke to Song and concluded that it wasn't really architected that would be useful for an optical enablement or a very easy one.
Yeah, just you still have the flight time of the optics.
Yeah.
Right, but the first thing it buys you is distance.
Yes.
So
which means you can.
So you very high radix switch.
Yeah.
Many port switch, and then you get distance between them. And
so,
if you don't play the distance card, then you're leaving something on the table.
Exactly right. So I think Ayer in their demo, they're still at 5 picojoules per bit, right? So it's like 4.7 plus a laser of 1 to 2, I guess. So they're in the 5 to 6 picojoules per bit. But so one of the things I was saying here is when you start to break down a 30 dB channel, which is what a PCI one is, you look at the segments of where the losses are. Would you believe the OEM module consumes 8 dB just to get out to the motherboard? And 5 of that 8 dB is for the package to get out the package to the module.
Right.
And so if you get rid of the package, you get 5 back. And then if you've got a chiplet world, you can actually put a chiplet directly above the connector, and you could, and I'm speaking to various other chiplet type IO companies, you could possibly do less than a picojoule per bit to get from a chiplet above a connector to an active cable. And that could be an active copper cable or a near packaged optics. Or you could do co-packaged optics where the light shines through the board if you put the optics out the bottom, and you could go straight into a connector, a passive optical connection, if you can get the alignment of when you mount the connector. So these are the dumb questions, and this what I'm just giving you here is a very brief summary of what I covered in the ODSA presentation I gave. But so these are the questions, but by me talking to every single vertical discipline, I get to understand what they can and can't do. and because I know every side of the silo walls, I know, I go, oh well, that we can handle that on the other side, but so I can see what needs to change, and that's the opportunity we have here. And in fact, to be honest, guys, although it's frustrating that we've been in concept for 2 years, I've had a wonderful opportunity to speak to so many experts in the different disciplines to tell me why something can't work, but how it possibly could work. And so we've got a number of refinements going on here. Like if you look at this module, those of you that have been here before knew we had 4 water connections. We've gone through the full water design of this now. It still needs proving firmly, but we've got 2 water connections now, and we have a good understanding, having spoken to a lot of the thermal people, about how this can work. It's not going to be 2-phase. I think that's too complicated. It's going to be single phase, but I feel a lot happier that we've got something at least that's firmly worth testing. And on the optics side, I'm just kicking off on that, and by speaking to all these people, I'm getting wiser by the minute, and so we'll see where that goes. But it's obviously critically important that we have optics is part of this architecture.
Well, I kind of view it, if you're putting in the effort, you might as well go for the next level, which is the optical stuff.
Yeah. No. Well, it's again, natively, it's in here in my cartoon mind. We have to make sure that the optical people say that, yeah, it's doable, and that's fine. But equally, Kevin, at the end of the day, if we can connect a traditional 10 picojoule per bit PCI channel with a couple of picojoules per bit, so let's not forget that going from this processor to one of these media, right? The media is that interface is CXL. That is 7 to 10 picojoules per bit. But the coupling of this, if we go to the chiplet on the substrate, I did the simulations with IBM. We can get this channel down to about 7 dB, and that we can drive it with about 1 to 2 picojoules per bit. And we can probably improve on that even more with some of the other ideas I've given. And I've talked to other companies like Elian about their low energy IO, and they reckon we could possibly get to less than a picojoule per bit electrically. And it looks like the silicon photonics has still got a ways to go to get down to that level. So if you're just talking between a memory module and your big processor, why not just electric?
Well, I think one of the things with the optical stuff, it's not necessarily all about power, because what you can do with optical is you can multiplex a lot of things at no cost.
Absolutely, you get the
and very low latency. So if I was going for this, I would say, I want the optical for low latency.
But that's the problem, Kevin. That's the problem, right? is I'll give you, for every person you give me, say we can do that right now, I'll give you another person that says it's still a decade away.
Yeah, the electron guys are never going to give up, and there's lots of room. I mean,
right.
Lots of room for what?
There's still the electron, just the receiver, and you can detect. I don't know what the noise floor is currently, but it's something like 3,000 electrons. You can build an amplifier that's that sensitive, right? So, the conversion. Nobody ever wants to talk about the conversion from electrons to photons and back, particularly. How many photons do you have to pump into it? You have to pump into twice as many photons to get the.
It's a question of what we're trying to build here. If it's a high performance compute platform, then what we're saying is we're trading power for speed. So to some extent,
yeah, right. So actually, so guys, perfect. You've just played exactly into my point. Is for everyone that says this is a piece of cake and we get so much more bandwidth, you're absolutely right, Kevin. Co-packaged optics is the only way to get that bandwidth through the roof.
Well, I'm not interested in the bandwidth. I'm interested in the latency.
Well, around the latency down, right?
Yeah, I mean, there's just too much of the computing.
But the point is, it's been 10 years away for the last 30 years.
Well, it's been more than that. And Terry retired because he said it just wasn't going to happen in his career.
Right.
And so I mean, but photon. obviously it's the way to go, but I can just tell you from being at this since like 92 is that the number of channels of optical doesn't need to double. It doesn't need to quadruple. It needs to go up by 2 orders of magnitudes.
Right.
2 order of magnitude.
Yeah. But there were a bunch of
Okay.
presentations last year at OCP on that stuff.
Yeah.
So I think
everything that's been talked about is not new.
yeah.
VCSELs
So
have been around forever. The only thing that's happened in the last 10 years is avalanche photodiodes in time of flight cameras. That's the only thing new that's happened.
There's MEMS tunable lasers.
Yeah, but they're big and they've been around for forever. MEMS lasers, I'll grant you that the lasers have gotten better,
Yeah.
but they're still this
so
big
we-
funky device.
Again,
We're getting-
I'm looking at low latency rather than low power.
we're getting in the weeds here, guys. But
Yeah,
I mean, it's a good point. My point is look, what we're proposing in OCP HPC isn't, you know, if we really want to do the Holy Grail, Kevin, then we need to build a Tesla dojo or a Cerebrus. These are the crazy ones.
I don't know if you need to go that far.
Well, exactly.
no, they're legitimate. They're legitimate.
Yeah,
There's
there's 2 sides to those boards and things. There's 2 ends
Right.
to the board. You don't
But
have
the
to all
point, my point is we can't go all the way. And my exact point on silicon photonics is everybody is just always crazy about co-packaged in chip optics. You know, they've now gone to co-packaged. Why don't we just think that we can make more of a continuous improvement?
One of the things, if you look at any of these things you plug in, is plugging in on one edge, and you've got 3 other edges and 2 surfaces to play
Right,
with.
obviously.
You're not using those in this particular architecture.
Yeah.
Right.
Hey guys, I'm gonna drop off.
Cerebrus uses the whole thing.
Right.
But
Sorry, John.
I'm gonna drop off. Have a good week.
Yeah. Well, we're
So-
at the top of the hour, but thank you.
Yeah.
All right. So much
Thanks
for
for-
giving the time back, huh?
Yeah.
So much. Yeah. There you go. That's good to
You
know.
have to leave. You have to leave.
All right. Bye.
I'll see you at OCP, Alan. If we don't have it ought to be a good week.
It should. Yeah. No. All right. Well, thanks, guys, and good discussion. We're just trying to. I think we're just trying to find this halfway house where we can help the migration to optics rather than this step change. There's a lot. It's the same with chiplets. We want to help the migration to chiplets. We want to help the migration to CXL, and I think we can do it with this approach.
I don't think there's a migration to CXL that's going to happen.
I know. If there isn't, it won't affect us, Kevin.
Standalone memory is such a bad idea.
Yeah. Alrighty.
Actually,
guys.
the PCIC, they
This
just launched the optical
Slide.
cable working group.
Yes.
So that's
And
for the
that's got its
CXL
own-
actually.
Yeah, and that's got its own challenges. But yeah, I think near packaged optics for that is good. And you've got Light Intelligence that have got a PCI optical cable, albeit 36 fibers, so it's a little bit looks expensive, but
Well, I mean, I would say the main problem with the optical stuff is that fiber connection.
yep,
That's
fiber
like
attach. Yeah.
That's the problem. But then, like free space optics and, you got free space RF stuff you can do. It's, do you really need it?
Yeah. Well, thanks for the link, Kevin. All right, guys. Well, we'll call that a wrap.
Alan, are the slides available?
So basically, just leave it a bit for Hisham. This is what I'm going to present at the OCP in a month. So I'd rather have the polished slides. So I mean, obviously the slides are here. I'll upload it to the wiki. I'll upload these to the wiki, so you'll see them.
Great. Thank you.
Okay.
Thank you.
All right, guys.
Okay, thank you.
Good presentation.